This video presentation is an introduction to the Dynamic Airborne Mission Communications System, Dynamics. Dynamics automatically creates optimized mission flight plans for aerial communication relay platforms. A prime example of such a platform is Beacon, the Battlefield Airborne Communications node. We'll start with a quick overview of Dynamics, the problem it's designed to solve, and a little bit about the technical approach that it uses. Then we'll show you a demonstration of the current Dynamics prototype software in action. This software integrates with the Joint Mission Planning System, JUMPS, to produce an effective orbit for an aerial communications relay supporting groups of ground, air, or maritime users. Here's a typical use case for Dynamics. A set of users on the ground and on the water are using radios to communicate with each other, forward command centers, and/or CONUS-based sites. A mission planner must select the orbit for the aerial communications platform to fly in order to best serve this set of users. As you can imagine, this is a complex task influenced by mission objectives and priorities, the capabilities of users' radios and the radios on the platform, terrain, weather, and potentially many other factors. What is the best orbit to serve users most effectively for a given mission? Current mission planning systems require the planner to input the waypoints of the planned orbit. The planner has to rely on his or her experience with past missions and make a best guess of what the most effective orbit will be. The complexity of this task is staggering if all the possible variables of radios, terrain, platform capabilities, subscriber locations, as well as the vital mission objectives and priorities are all factored in. The planner must be a multidisciplinary wizard, and the actual effectiveness of the orbit that is eventually selected is very hard to determine. Dynamics changes the basic planning approach. Now the planner only needs to input the locations of subscriber nodes and relative priorities. This data may even already exist in a force-level planning system, allowing Dynamics to simply import the subscriber data. Dynamics then uses the subscriber data along with information about the terrain, radios, and aerial platform capabilities to construct a model of the entire mission. Using mathematical optimization techniques, Dynamics can then try out hundreds or thousands of different orbits in order to find the one that is most effective. The waypoints of this optimized orbit are then injected back into the mission planning system automatically. The presence of the model also allows Dynamics to predict how well and at what times individual users will receive connectivity. And this can be important for factors such as maximizing the battery life of handheld radios. Why turn on your radio now if you know you won't have any coverage for another 45 minutes? Let's start looking at the demo of the prototype Dynamics system that we've integrated with JUMPS. You can see the locations of 8 different subscriber nodes which we'll be using in this demo scenario. The nodes are displayed in JUMPS near Elmendorf Air Force Base in Alaska. The rugged terrain of the southern Alaskan coast is exactly the kind of challenging situation that makes Dynamics so useful. In this demo scenario, our 8 subscribers are in 3 groups as shown here. Group A and Group B need a voice bridge between each other, and both groups require a voice bridge to Group C. Note that Group C only has one member and, as we'll see in a moment, that one member is in a particularly difficult terrain location. We can switch to a 3D view in STK, and you can see that that single node in Group C is situated in a deep valley, which will constrain its ability to communicate with the airborne platform. If we just naively choose an orbit that consists of a circle centered over the entire set of subscribers as shown here, we get poor coverage for our 3 voice bridges. The link between Groups A and B gets about 56% coverage, but the other 2 voice bridges get no coverage at all. This amounts to about 19% average coverage with, of course, coverage deviating substantially from group to group. Dynamics can find a much better flight path than this. We'll set Dynamics to use a circular orbit and to vary the diameter between 30 and 120 miles and the altitude between flight levels 200 and 440. Once we start the optimization process, we'll switch back to the STK modeling system display and you can see that a variety of different orbits are being tested for the coverage they provide. We're simultaneously showing a 3D view on the left and a top-down 2D view here on the right. The mathematical optimization process searches through candidate orbits as efficiently as it can to find a few good candidates, and then tries to make those good orbits even better. You can see that it quickly determines that good candidates must favor the south, so that they can pretty much fly directly over that subscriber node which is furthest south, which makes sense given its position in that deep valley. You can see that overall the average coverage has improved from the original 19% to over 68%, with excellent coverage provided to all 3 of the voice bridge groups. Remember that for our naively selected orbit, the second 2 groups had no coverage at all. The deviation in coverage has also decreased substantially. Better and smoother coverage is the result of this dynamics-generated orbit. We are convinced of the viability of the dynamics approach to orbit optimization for aerial communications relay platforms. As we have shown in this brief demonstration, we are able to consistently improve and smooth coverage for ground, air, and maritime subscriber nodes.